Okay, I'm set. Welcome to lecture 9 of the planets. This is going to be a special lecture. We're going to finish talking about the nature of light with a special attention on the emission of infrared light that comes from solid objects like a planet or the chairs in the room or indeed your human body. And we're going to talk about how infrared light can serve as a diagnostic of the properties of those types of objects. Now, before I tell you about that, I'm going to give you a review of the last lecture. And before I do that, I'm going to tell you about some of your obligations in the next 3 or 4 days. One is to do the homework in Chapter 5. And it's due tomorrow, of course, as always, tomorrow, Friday at 6 p.m. So that's due, as always. And then there's this midterm that is coming up on Tuesday. The next class meeting here will be a midterm. And as I mentioned last time, but I'll repeat it now, it will be a multiple choice exam. There'll be about 30 questions or so. And it will cover all 5 of the chapters we've covered, chapters 1 through 5, including today's lecture, and the homework that also covers today's lecture. And so, by all means, this is a good time to organize the next 4 or 5 days of your life, not just to finish the homework, but to find good times to study. People always ask me, well, what's the best way to study for the midterm? And I have a few suggestions. The first and foremost suggestion is find a big block of time, maybe 3 hours, and go through all 5 chapters. The way I used to study as a student is I would start at page 1 and look at the page and ask myself, do I understand the basic ideas on that page? Are the concepts all clear to me? The reasoning? The explanations. And if they were, I would go to the next page. But if not, I would concentrate on that page, read a paragraph, try to remind myself of what I knew back when I was studying that chapter. And after I convinced myself that I really understood the idea, the concept, then I would go to the next page and do that page after page. That way I wasn't really reading each page, but sort of skimming. But in a critical way. The critical thing you have to do is be sort of asking yourself, do I understand what's on that page? Do I really understand it? And if not, read it until you do. And if you still don't understand it, that's a good topic to bring to office hours or the discussion section, or send an email to a GSI or to me and ask a question. So it's a great way to study, to just go through the first 5 chapters using the material as a way to prompt you as to whether you really understand the issues. And then, of course, the other way to study is to go to the lecture notes that are posted online. The exam will certainly emphasize those concepts and maybe a few equations that are in the lecture notes. So there, too, you can go slide by slide as posted and ask yourself, do I basically understand the ideas on this slide? And if you do, just go on. And if not, spend more time. Maybe go back to the book. Okay? And we're going to draw some of the midterm questions from the homework. So a good way to study is to go back and redo homework problems. Make sure you really understand each one of them. And if you don't, again, zoom in and try to understand that homework question, because it may come back to haunt you. Any questions about the midterm at this stage? And feel free to send us emails if you do have any questions. Let me spend a little more time than usual reviewing last Tuesday's lecture. It was such an important lecture talking about the nature of light as a wave, as a photon. And so I'll remind you that light comes in all colors, otherwise known as wavelengths or frequencies. And the visible light that your human eye can see is just a sliver of the entire electromagnetic spectrum with all of its wavelengths. The visible wavelengths are just this tiny little regime of wavelengths from 400 nanometers to 700 nanometers of wavelength. Remember, wavelength is the distance between the wave crests, the tops of successive waves in the light wave. And we showed some videos of the nature of light, just to remind you that light has both a wavelength, the distance between wave crests, and a frequency. The frequency of light is the number of wave crests that pass by you per minute or per second. So there's a wavelength and a frequency, and they're related to each other, frequency and wavelength, by the speed of light. The product, if we multiply the wavelength times the frequency, you always get the speed of light for light waves. And that's, by the way, true in general for waves. The frequency times the wavelength is the speed of the wave. And the speed of light is incredibly fast, as you know, 300,000 kilometers per second. And as I mentioned, our human eyes have been adapted by evolution to be sensitive to just the wavelengths blue, green, yellow, and red, because those are the wavelengths of light that our sun emits. So our eyes have evolved over millions of years to be very sensitive to the very light that our host star emits. And then we talked about light as a particle. You can think of light as an infinitesimal tiny particle that moves at the speed of light, but despite moving so fast, it still has a wavelength and a frequency. These photons, as they're called, have energy. And I wrote down an equation for the energy of a photon. It's proportional to the frequency, but also proportional to a constant of nature, Planck's constant, written as an h. So this was a great discovery about 90 or so years ago, 90 or 100 years ago, that light can be described as a particle, not just a wave, like a water wave. And that particle, the photon, has energy proportional to the frequency, and obviously, therefore, inversely proportional to the wavelength of light. Now, the most important concept, and actually the most sophisticated one, was an issue of quantum mechanics, and I'm going to show a little video about it in a second. And the idea is that an atom, indeed any of the atoms that you see over here on the periodic table, have electrons buzzing around outside, and the electrons reside in certain specific energy levels. And those energy levels have a certain energy that is assigned to the electron when it's there. And here's shown for a schematic the hydrogen atom. This is the model I keep in my mind. There's energy levels. The electron can be in any one of those energy levels. You don't know which one. It usually falls down to the lowest energy level if it has the chance. But electrons in any energy level can absorb energy. An electron can suffer from a collision with another atom that bangs into that host atom. Or maybe a photon delivers energy, popping the electron from its current energy level to a higher energy level. And when the electron goes from its current level, like level 2, to level 3, it's now got more energy. Electrons don't like to be there, so they naturally drop down. But the point that I'm emphasizing here is electrons can absorb energy from either collisions or from a photon. And then that energy excites the electron to its higher energy level from there to there. And now that electron excited at a higher energy has the preference, of course, to drop down to a lower energy level. Just like a ball naturally rolls downhill to a lower gravitational energy, an electron will roll downhill from energy level to energy level like a ball going down stairs, steps, ka-tink, 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 going from one energy level to the next, losing energy as it does. And then to conserve energy, when the electron drops down to lower energy levels, that electron in the process spits off a photon that has an energy equal to the difference in the energy levels that it's dropping down to. So only those photons whose energies equal the difference in electron energy levels can be emitted or absorbed. The electron can move from one energy level to the next. It can absorb a certain photon of a certain energy, popping it up to the next energy level that's a certain delta energy away. And then when the electron drops back down, it spits off a photon of the same energy, equal to that energy difference. I'm going to show a little 6-minute video that it's a little lengthy, for which I apologize, but the guy doing the video does such a clear job that I wanted to spend the 6 minutes and give you a chance to stop there. I really like that video. It explains very clearly how the structure of an atom works and how the energy levels within an atom lead to electrons going from one energy level to another, absorbing light of certain frequencies or energies, or emitting light of certain energies or frequencies. So it's a very powerful, I think, a very powerful concept which tells us how light gets generated in general. From the sun or from a light bulb, it's always atoms that are dropping from a higher energy level to a lower energy level. And when the electrons do that, they conserve energy by spitting off a photon of the appropriate energy corresponding to the drop in energy of the electron. Now, I'd like to talk about absorption too. And so in this little video, we're going to talk about the absorption of light. And the idea is shown here. Suppose you have a planet or a star emitting light, and here are the photons coming from that emitter. It could even be a light bulb. And then if the photons were detected by a telescope, you would see all of the wavelengths of light that are emitted by that star or planet or light bulb as they get collected at the telescope. But what if you put some gas in between the source of light and the telescope? That gas consists of atoms of a certain type: hydrogen, carbon, oxygen, iron. And those atoms will only absorb photons that have a certain specific set of energies, namely the energies that correspond to an energy difference between a lower energy level and a higher energy level. So whatever types of atoms are in that cloud determine what energy levels there are in those atoms, and therefore which energy photons of which energies, can be absorbed by those atoms. So I'll summarize that here. Atoms absorb photons whose energies, i.e. wavelengths, match the energy difference between the current energy level and the higher energy level. The electron starts at a lower energy level and gets excited up to a higher energy level. And so the resulting spectrum has all of the wavelengths of light that was emitted by the original star or planet or light bulb. All of the wavelengths were emitted by it, but it will be missing those wavelengths, those specific wavelengths or energies that these particular atoms had the ability to absorb due to the energy levels in those atoms. So you get a spectrum of colors with certain specific wavelengths or energies absorbed away. And the fingerprint, if you will, of those atoms is the set of frequencies that are absorbed. The certain specific colors that are absorbed tell you what type of atom must be in this gas doing the absorbing. So that's the basic idea. Okay, what this all means is that if you take a spectrum of any other object whether it's an astronomical object or maybe something here on the planet Earth, you can determine what types of atoms that object is made of by the emission or the absorption spectral lines that you detect. Because certain atoms have certain energy levels, and no two atoms have the same energy levels, a little like snowflakes. Okay, even though we just spent a half an hour on that, I was glad we did it because it's such an important idea. I now want to talk about a different topic of light, and it's the type of light that gets emitted by solid objects, opaque objects. Solid objects are different. And you know a little bit about the emission of light from solid, warm objects because you've all seen a light bulb. When it starts, when you turn on a light bulb, initially it's kind of a ruddy red color. There's the filament of the incandescent light bulb. And then as the light bulb warms up, it gets brighter and the color changes, i.e. the typical frequencies of light change. I'll say that again. As a light bulb warms up, it gets brighter and the typical wavelengths of light change from long wavelength red light to shorter wavelength green and bluish light. And that's going to be the topic for the next 5 or 6 slides. All of you have had experience with what I call, and what is normally called, thermal emission of light from solid or opaque objects. Have you ever seen an electric stove, how it starts warming up? An electric stove looks a little like this. When it starts warming up, it's a sort of dull red, and as the electric stove heats up, it gets brighter and whiter from its initial red color. The same is true of coals on a fire. They're glowing by thermal emission. The brightest places, the most brilliant white light is coming from the hottest embers in the fire. The hotter the embers, the brighter they glow, and the whiter the color, from ruddy red up to more and more bluish color. And similarly, lava is glowing by thermal emission. It's warm, it's hot, and even though it's not solid, it is opaque. And so lava glows. You can tell just intuitively which parts of the lava are hottest. The cool lava is dark colored, and the hottest lava is brighter and less red and more of the full rainbow of colors. Here are some other examples. Your human body emits thermal light all the time, every minute of your life. Here's a thermal emission picture of a human being. You can tell which parts of her body are the hottest and which parts are the coolest. Cool regions emit less thermal light. Hot regions of her body emit more thermal light. In the case of a human body, at the temperatures of our bodies, we are emitting infrared light. That's why you don't see me glowing or anybody else glowing. We are glowing. It's just that your human eye, unfortunately, is not sensitive to infrared light. Of course, other animals emit infrared light too. You can tell which parts of the dog are hot and which parts are cooler. The dog has fur to keep it cool and keep it at a constant temperature, whereas the mouth and the eyes expose the inner higher temperature of the workings of the dog's body. And the same is true of a house. Houses are insulated like a dog's fur, and so the parts of the house that are darker in infrared light are not emitting very much light because they're cooled by the outside air. But inside the house, you want it to be warm. And of course, at the location of the windows, you see the infrared light streaming out of the house. The thermal emission is high because it's warm inside the house. And in effect, you're losing energy. Your house is losing energy when you have cracks in the walls or windows. The thermal infrared light can stream out of your house, and you can do an energy budget analysis if you want your house to be very energy efficient, conserving energy. Well, you would want to do something about windows and cracks to make sure that you're losing less light. And there's a relationship that relates the temperature of the object and the amount of thermal emission. And that relationship is shown here, that the amount of thermal emission of light is equal to some constant, forget about it, 6 times 10 to the minus 8, that doesn't matter, but multiplied by the temperature to the 4th power. So when you increase the temperature of an object, the amount of thermal emission emitted by that object, the infrared light, the thermal infrared light from that object, increases as temperature to the 4th power. So for example, if you double the temperature, and we are using here a temperature scale called Kelvin. You've all heard about the Kelvin scale from your chemistry class in high school. In the Kelvin temperature scale, when the temperature doubles, how much does the thermal emission go up? Well, by 2 to the 4th power. What's 2 to the 4th power? 2 times 2 is 4, times 2 is 8, times 2 is 16. So if an object doubles its temperature, the amount of thermal emission goes up by a factor of 16, a huge increase. So hot things are very efficient at emitting lots of infrared light. You can, of course, measure the amount of infrared thermal emission coming from an object, like this human being, by using an infrared camera. They're fairly expensive. They cost a few $1,000s, but you can buy a thermal infrared camera to measure objects. The Earth as a planet emits infrared light. Why? Because the Earth is warm. And where is the Earth the warmest? At the equator. And so if you take a thermal infrared picture of the planet Earth, you'll see more emission of that thermal infrared light near the equator, less at the temperate regions, and very little at the poles. And the reason, of course, is that it's hotter at the equator, and you now know the formula that the amount of thermal emission of light is proportional to the temperature to the 4th power. So the equator is where it's warmer and where it also emits the most light. So let me summarize everything that you've heard me say. I'll say it in words here. Warm objects, any object with any temperature, emits infrared light or radio waves. If it's hot enough, it might be visible light. Examples are embers of a fire or an electric stove. Hotter objects emit more thermal energy per square meter, if you will, and the amount of energy is proportional to temperature to the 4th power, as I've already mentioned. Furthermore, in addition to those 2 points, there's a question of what wavelength of light the light comes out at in thermal emission. And the answer is that hotter objects, as I have said, emit more of their light in bluer photons, i.e. higher energy photons. This makes sense. A high energy, a high temperature object, a hot object, emits photons that have higher energy, i.e. bluer. And a cooler object emits lower energy photons, i.e. redder. And there's a relationship which I'll just tell you about. It's one of the most powerful in this field. The average wavelength of light emitted in thermal energy, the average wavelength is proportional to 1 divided by the temperature. The higher the temperature, the shorter the wavelength of light. For example, a high temperature object, as you crank up the temperature on something, it emits bluer and bluer photons systematically compared to the red photons. Conversely, a low temperature object thermally emits longer wavelength photons. And so that's the basic idea. Actually, I have a little example of this, and then I'm going to show a demo, I hope. Yeah. So this is a graph, and hang on to your hats. It's a graph showing the intensity of thermal emission as a function of the wavelength of light. This is a new kind of graph. We're going to see a few of them in today's lecture, so check this one out. How much light is emitted in the form of energy, light energy, thermal energy, for different wavelengths of light, with the units being nanometers, a billionth of a meter. Here's the visible spectrum: blue, green, yellow, orange, red, right in here. And this graph right there shows how much light is emitted at different wavelengths. This is a very sophisticated graph and a very powerful graph. People in physics, chemistry, biology, and the medical community examine graphs exactly like this to interpret and diagnose various objects that they're studying. So this graph here shows you how much light comes out at different wavelengths. Where's the peak amount of energy? Well, a wavelength of about 1,000 nanometers. That's the wavelength of light at which most of the energy is thermally emitted for this particular example. Now, what I can do is show you what happens when I change the temperature. And the temperature is shown right here. It's 2.24 times 10 to the 3. Let me translate that. That's, of course, 2,240 degrees Kelvin. That's pretty hot, hotter than an oven. And at that temperature, this graph shows how much light is emitted at different wavelengths. Notice something profound. Thermal emission, unlike an individual atom, thermal emission emits light at all wavelengths. It keeps going off and to the right and off to the left. In thermal emission, there is light of all wavelengths: blue, green, yellow, and red, just different amounts of those wavelengths. Now, notice what happens when I change the temperature. So I'm now going to use this slider and change the temperature from its current 2,240 degrees. I'll make it hotter. Notice what happens to the graph, the intensity of light at each wavelength, when I make the object hotter. It gets more intense. The thermal emission is greater. There's brighter, more light being emitted by the object. And the peak is now over here. The wavelength at which most of the light is emitted has shifted over to here from where it used to be. Let me put it back around here or so. The peak used to be at 1,000 nanometers, but when I made the object hotter, it got brighter, and the peak wavelength, the wavelength at which most of the light was emitted, is a shorter wavelength of light. What does that mean? Well, remember, shorter wavelength photons are photons that have higher energy. So that makes sense. Hotter objects emit photons that typically have higher energy. So two things happened when you change the temperature of an object. The thermal emission gets brighter, and the peak wavelength goes to shorter or more energetic, shorter wavelengths or more energetic photons. Let me make the object cooler now. If we make the object get cooler and cooler and cooler, like say over here, now the thermal emission is less. You see the height of the graph is less than it was. The intensity of the light is less than it was. And the peak wavelength has now shifted to a longer wavelength. Remember, I told you the wavelength, the average wavelength, is proportional to 1 divided by the temperature. So a lower temperature means longer wavelength, and that's what happened. Notice too that the amount of light in visible light is pretty low. Most of the light is in the infrared, and so it is with your human body. Even if your human body were, 700 degrees Kelvin, which it isn't that hot, but even if it were, your human body would barely glow in visible light over here, but your body would mostly glow in infrared light. Now, I want to show a demo that illustrates all this, and boy, do I hope this demo works. And to do that, I might need some help. Let's try to get it to go. I brought an infrared camera today, and I hope it shows up on the upper screen, not just the lower screen. Any idea what I should do to make the upper screen work? I'm glad the lower screen is working. System is currently in operator mode. I don't know what that means. Cool. I don't know what all that, oh, I see. It's here too. So you're seeing what the camera sees. If you can see this little tiny picture here, that's exactly what you're seeing up there. Now, human bodies emit infrared light, and so I can point at people in the front row or in the back rows, but let's go back to the front row. And I think I'll move around a little bit. Oh, that's my fault. I pulled the plug out. I think. I may need your help in the back if you get a chance to help me, because now I have to figure out where this plug goes. Here comes my trusty helper. Let's see here. I think I pulled this plug out.
Oh, this is supposed to go in.
Yeah. Yeah.
Yep. Here we go.
Were these connected to anything? I don't think so. I have confidence.
There you go. Yeah.
Yay.
I think I could get rid of.
Yeah? Yeah. I've never been able to get rid of that either. We're trying to get rid of the words that are in the way. Yeah, I can't get rid of it. It's okay. So we're back online, and now you can see what people look like when they're just sitting normally. I used to know how to focus this, but I'm not sure I know how to focus it anymore. I've forgotten. Let me try a few things. Yeah, I don't know. But anyway, you get the idea. You can actually see the glow of all of you. I'm pointing at all of you now. And you can see that faces are relatively, if people are blocking the light. Yes, sir, this does look through clothing. No, it doesn't. You can see that faces are relatively hot. People are waving. People are flying. Now, the interesting thing is that this is sensitive to visible light with a wavelength that's about 10 times longer than the light that you normally can see. So let me say that again. It's visible to infrared light that has a wavelength about 10 times longer than your human eye is sensitive to. It's such different light, infrared light, that it behaves in a different way than you might expect. So let me point it at myself. Does that work? And maybe I would like to get rid of that X, but I don't know how to get rid of the X. Do you have any idea? Ooh, we have another expert help.
Oh, no, not expert.
The X didn't used to be there, I think.
Oh, no.
Uh-oh.
Here, hold on.
If she breaks it, it's her fault.
Maybe we can.
You're trying to cycle the power.
Yeah.
Yeah. Should go off. We can't even turn it off now.
Oh, no.
Uh-oh. Yeah. This happened to me once, too, when it went into the sort of black and white mode, and then I couldn't get it out of the black and white mode. Ah, what's that?
Oh.
That's bad. I don't know why there's that X in the middle of the picture. It didn't used to be there.
Yeah, I think.
We're pressing all of the buttons on the camera hoping to get, oh, yay.
But now it's weird.
Yeah. Uh-oh, the X is back. You're good at this, though, I got to tell you.
No. I think it was in their setup. Fusion, yeah. It won't change.
YouTube isn't going to save us this time.
Click those arrows. It won't hit the arrows.
Yeah, it won't do the arrows. Can we cycle the power again? Is that possible?
It's not.
This is going to be worth it, I promise.
Oh.
Ah, something good is happening. Yay! She's a genius. Okay, now let me try again. I'm going to try one thing. Oh, there we go. Yeah, it looks different, doesn't it? Yeah. All right, before it kills us again, let me point at me. Try to do it delicately. Can you see me? Barely. It's sort of a weird outline. Yeah. It's got a funny temperature scale. Do you have any idea how to change the temperature scale? It did invert the heat thing. I don't know how to change that. Uh-oh, she went back to setup mode. That scares us.
That's not it.
It's normally not this hard.
I wish I could just. Oh my gosh. Can you just turn this off?
Yeah, okay, we're going to try to cycle the power now. Oh, that was good, I think.
Is it back on the.
Oh, that was good. Isn't that good?
Yeah, 1 second.
Oh, yeah, that's good. I'm optimistic.
Now the squares behind it. There you go.
Uh-huh.
And then video, and then the. Is that it?
Yeah.
There you go.
All right. Oh, it's still inverted. We could leave it like this. I think it's okay.
Sorry, I don't know why.
Yeah, I don't know why it's doing this either. We can leave it. It's okay. All right, so here's what we're going to do. This actually has just got large dynamic range. What I'm going to do is point it at me again. And I think you can see me this way. And now I'm going to do something interesting. I brought some transparent plexiglass, and I'm going to put it in front of the camera, and we'll see what happens. It's actually completely opaque. You can't see me at all. There I am, emitting infrared light. You see my... And here's with the plexiglass. It just blocks it out completely. This is utterly opaque in plexiglass. Now, I also brought something opaque in visible light, which is this bag. And what I'm going to do is put this black plastic bag over my head. I think you'll agree that you can't see me when I have the bag over my head. You can't see me, right? Now, what I'm going to do is point the infrared camera at me. Hang on. So actually this black plastic, even though it's opaque in visible light, it's utterly transparent in infrared light. So you can see that the light waves have the ability to transmit themselves through certain objects where you wouldn't expect it to based on visible light. So these infrared cameras are quite powerful. And of course, in addition, when I have the scale set right, I could measure the temperatures of your bodies on an individual basis, and even with resolution, measure the temperature of parts of your body. So I think I'll give up on this for now. This was a lot of fun. I love this little thing. I've actually taken this camera to my house and used it to find out where there are leaks of energy in my house. You don't have to pay for someone, you just use your own infrared camera, right? Okay. Back at the ranch. So now you can sort of see what I was talking about with this graph. That graph tells you how much light is emitted by objects of different temperatures. Your human body at, room temperature, you're a little warmer than room temperature, is glowing like mad, but your human body is glowing in infrared light, thermal emission, which is peaking in this function here that you see, peaking at wavelengths that are in the infrared and can be picked up by an infrared camera. All of your life, you're emitting energy, photons, albeit infrared photons. And part of the reason you have to eat breakfast, lunch, and dinner is that your body is emitting energy, and so you have to eat to take in energy so that your body can continue to be warm, and of course it loses energy by this thermal emission. Yeah? We emit a little bit of radio waves. You can see in that functional form that I'll point to it. Over here at long wavelengths, our bodies are still emitting some long wavelength radio waves right way over here. Yep. Okay? Yeah.
Do we have a camera to detect those too?
I think the question is, do we have a camera to detect radio waves? Yeah, there are radio telescopes that can detect and take pictures of objects that are emitting radio waves. That's what radio telescopes do. Okay? So I can summarize everything that I've said in the lecture so far, which is hot objects emit more light in thermal emission, and the amount of energy emitted is proportional to temperature to the fourth power. Hotter objects emit shorter wavelength photons, higher energy photons, and here's that formula that the typical wavelength is inversely proportional to temperature. Now, there's one last key point in today's lecture. It's going to take me 4 or 5 minutes to make it. This is really spectacular. If you would like to understand a planet, or a moon, or the rings of Saturn, or some new discovery that you've just made somewhere else in the solar system, you can take a spectrum of that object. And the word spectrum means that you measure the intensity of light on the vertical axis as a function of, in other words, at different wavelengths of light. Short wavelengths like ultraviolet and blue, longer wavelengths like red, and then even longer wavelengths like the infrared. And this graph shows you how much light is emitted at different wavelengths. And as you can see from this graph, there's a lot of structure in this graph. There are peaks and valleys and wiggly things, and I'd like to explain to you what all of it means. You should be able to analyze this graph, the spectrum as it's called, the amount of light at different wavelengths. By studying the spectrum of an object, you should be able to learn what atoms it's composed of, what temperature it has, and even, by measuring the Doppler effect, the speed of the object. And so here's how it works. Here's a generic spectrum of a planet or a comet or an asteroid or a moon. And you see this intensity of light with different wavelengths has peaks and valleys and more peaks. What do they all mean? Well, let me tell you. Right here is a big peak in the blue, green, and red. Why would a planet, a comet, an asteroid, or a moon have so much light at visible wavelengths? Well, the answer is it's simply reflecting light coming from the sun. Sunlight streams through the solar system, hits a planet or a moon, and that planet or moon reflects the sunlight that hits it. And so this big peak here is nothing more than the reflection of sunlight. And you already know that the sun emits some blue light, lots of green and yellow light, and then less and less red light and even less infrared light. So point number one is an object in the solar system reflects light from the sun. That's obvious. But objects in the solar system, like a planet or a moon, are also warm. And because they're warm, they emit thermally. There's thermal emission. And of course, a warm planet like the Earth or Saturn or a warm moon orbiting Neptune will have a cooler temperature, and so the thermal emission peaks way out here in the infrared, just like we were talking about. And so you can always tell what the thermal emission is compared to the reflected sunlight, because the planet or the moon is typically quite cooler than our sun, which is blazing hot. The sun is so hot that its thermal emission is indeed this curve here, albeit that's being reflected light. In addition, there are some funny absorption spectral features right here. That represents absorption in the atmosphere of the planet. Any self-respecting planet will have an atmosphere, maybe some of them don't. And then when the sunlight hits that planet, the gases made of atoms and molecules will absorb some of that sunlight. But remember, atoms and molecules absorb sunlight, or any kind of light, at specific wavelengths, a set of specific wavelengths, or in other words, certain energies of the photons. And so this funny sawtooth-like looking pattern represents the specific wavelengths at which the light is absorbed due to the atoms that are in the atmosphere of that planet, or molecules, either way. So you can analyze the chemical composition, the types of atoms that are in the atmosphere, from exactly which wavelengths are absorbed. So to summarize, this spectrum not only tells you about the sun, that's the sunlight reflecting off of it, but you can learn something about the chemical composition of the atmosphere from the absorption of wavelengths. You can certainly learn the temperature of the planet, because remember, the amount of thermal emission is related to temperature, and the peak wavelength of that thermal emission, the wavelength where the intensity is highest, is directly related inversely to the temperature. So you can actually measure the temperature of the planet or the moon two different ways. And then finally, you could measure, if you wanted, the Doppler effect of these spectral lines, telling you the speed of this planet by the amount of the Doppler shift of those spectral lines. So you have an enormous amount of information you can get by just taking a spectrum of the object of interest, even if you don't know anything about it. I'd like to finish today's lecture with just 2 or 3 slides that are on a totally new topic, and you're not responsible for it on the midterm. But I just wanted to touch on how it is our solar system formed. And the answer is that you can learn something about how our solar system formed by the properties of our solar system. Notice that our solar system, with its 8 major planets, has some amazing properties. The orbits are nearly circular. The planets all lie in a flattened plane, the ecliptic plane. And all of the planets orbit the sun in a counterclockwise direction, not randomly. They even typically spin in the counterclockwise direction. Even the moon goes around the Earth in that counterclockwise direction. So it's quite remarkable that the solar system has this geometrical consistency of a flat plane and spin direction. In addition, the inner planets are small and rocky, and the outer planets are large and gaseous. So we should be able to ask the question, how did our solar system form to have this architecture, if you will? And the answer is that you can learn something about the formation of our solar system by looking out into space and seeing how other solar systems are forming in our Milky Way galaxy. And they in fact form from the gas and dust in between the stars. And you can see it clearly on a dark night. You look up into the night sky, and these dark patches that you see everywhere represent the gas and the dust blocking the starlight. And that's the gas and dust out of which young stars and their attendant planets are forming. The gas and dust floating between the stars in our galaxy, you can see them clearly here, gas and dust just floating, gravitationally contracts down to a star by gravity, and by conserving angular momentum, the planets then condense out of the remaining gas and dust as gravity pulls that material in. One last comment before I quit today. I noticed that the weather turned for the better. It was quite clear when I came in to Pimentel. I think tonight and probably the next few nights will be very good opportunities to try to detect Saturn, Mars, and Antares. So try to take a peek at the horizon after sunset.